Welcome to this lesson on motion sensing in the course on industrial automation and control. So, today our instructional objectives are that we will motion means position, velocity, acceleration. So, today we will, and there are various types of motion sensing instruments, but we will only look at those which are of relatively more importance in the context of industrial automation. There are other application areas like aerospace where some of the other kinds of sensors are very important. They are also motion sensors, but we will not look at them per se. So, the first objective is that there are some basic techniques by which we will see that how changes in position can be converted to changes in resistance, changes in capacitance, or change in inductance. Sometimes changes in mutual inductance. So, and then once we, so that is the first step where we are converting this mechanical motion into an electrical parameter change. After that we can employ standard signal conditioning circuitry for which are there for sensing these changes. So, we will learn about the signal conditioning circuitry at another in another lesson. So, right now we will show how predominantly we will show that how these how the motion actually translates into changes of resistance, capacitance or inductance. So, that is the second. One of the major applications is measuring speeds of rotating machines, because rotating machines are a very important class of actuators in the industry and they have to be controlled. So, for the purpose of controlling, it is very important that we measure their not only their position, but also because position measurement is basically angular position measurement. So, we not only measure their position, but we also measure their speed. So, we will look at some of the methods of measuring speeds of rotating machines. We will also look at some optical methods of measuring speed. Optical methods are very good in some respects and not so good in some others, but they are a distinct class of methods. So, we will have a brief look at that, and we will also look at measurement of acceleration, which is typically done in the industrial context by piezoelectric sensors. So, having said that, let us first look at position sensing. So, let us look at resistive transducers first. Resistive transducer, the basic principle of sensing position using resistance transducers is that uses a 3-terminal resistor. So, what you have? So, what you have is, let's look at this. So, what you have is you have a 3-terminal resistance. So, there are 2 fixed terminals and there is one variable terminal. This terminal, this position can move. So, movable position, sometimes we call it a jockey. Now, so obviously as this moves, it can move either in a linear fashion or in an angular fashion. As it will move, naturally the resistance between these 2 terminals will change. So, it can work either as a resistance or it can work as a voltage divider, in which case if you supply voltage across a fixed voltage, then the voltage across these 2 terminals, this is V out, will change as you move the position. So, basically this principle is what is used for resistive transducers. Now naturally, since there is a point which has to constantly move on this resistance, this resistance can be either a wire wound type where on some former thin wires are many turns of a thin wire are wound, so that if you have a small displacement, you will have a small resistance change. So, you generally have a good resolution, or you can sometimes have a resistance film on which a movable contact will move. In any case, there is going to be a contact and this contact is continuously going to move. So, contact problems tend to develop. There is problem of contact potential, there may be problems of contact loss. So, this is one of the biggest problems, although this transducer is actually very cheap, but this is one of the biggest problems of this transducer. So, so you have, for example, you have resolution, sensitivity, tempo problems. So if you have these, the sensitivity may actually depend on how much current you are sensing through these resistances. That if you send too much current, temperature of the wire will rise. So the resistance change will now be affected by what is known as self-heating error. So these transducers, although they are cheap, they are often affected by such problems. This is a typical configuration for the linear motion case. So as you can see that this is the exciting voltage. It can be DC or it can be AC also, and this is the output voltage. So as it moves towards this, the voltage increases, and as it moves towards this point, the voltage decreases. Similarly, you can also use a similar configuration for angular current sensing, angular motion sensing. So for example, this is a case where you have a single turn angular potentiometer. So nothing, only thing is that now the movable jockey, rather than moving in a linear fashion, is going to move in an angular fashion, and then the resistance coil is also wound in an angular fashion. That is the only change. As such, circuit wise there is no change. So this is mainly about resistive transducers. Now we come to capacitive transducers. So in capacitive transducers, due to the motion, there is going to be a capacitance change, right? So now we know that typically, if you take the simplest case of a parallel plate capacitor, for example, let me explain this. So why this is changing. So okay, we can write here itself. So the capacitance is given by epsilon A by D for a parallel plate capacitor. So change in capacitance can occur either due to the change in the area, or due to a change in the plate separation, or also due to a change in the dielectric medium, right. So these principles, all three principles actually can be used for making capacitive sensors. In the case of motion sensing, typically change in area, I mean geometrical configurations are used where due to the motion either the area changes or the displacement changes. Now you have to note that if there is a change in area, then the change in capacitance is actually linear with respect to the change in area, while it is not linear with respect to the change in D. So this must be remembered, because as we explained that we generally look forward to a linear characteristic in sensors, basically because of ease of use. So now we come to the capacitive transducer. So you see this is one particular configuration. So here what is happening is that you have two cylinders, so which are where one is fixed and the other keeps moving. So you can well understand that the area, basically the capacitance plate which is going to form is on the intersecting part of the area. So as it moves, so this area is going to vary, right. So this is a typical variable area geometry, while if you have two plates and then one plate, for example, suppose one plate is fixed and then the other plate is movable and it keeps moving like this, then there is a constant D variation and there is a capacitance variation with respect to D, only noting that the variation is not linear. It is approximately linear when this change in D is small. So therefore this geometry of variable distance can be used for small displacement sensing, I mean keeping the sensor as linear. This is a case where you have a push-pull configuration. Sometimes we find that push-pull configurations can actually cancel some non-linearities. So not only that, they will also enhance the sensitivity. So here what is being done is that what is being done is that there are two capacitances which are formed. So you know this forms one of the capacitances which is formed between these two terminals, and this is forming another capacitance which is forming between these two terminals. And as this is moving here, if it moves to left, then the area is increasing, so this capacitance is increasing, and by an equal amount this capacitance is decreasing, because the area increase of this is exactly equal to the area decrease of this. So you can say that it is, if it is C plus delta C, then this is going to be C minus delta C. So such a configuration is called a differential output or push pull configuration, because of obvious symmetries. You can either push it or pull it, and as we shall see in our signal conditioning lessons, that there are certain benefits if you have push pull configurations in terms of nonlinearity as well as in terms of sensitivity. And also, you know, sometimes tolerance with respect to other kinds of inputs, like interfering inputs like temperature, etc. So for these reasons, sometimes the push pull configuration is preferred, and this is a push pull configuration for capacitive, you know, motion sensing. So similarly, this shows a push pull configuration for the variable plate separation case. So here there are actually these are the two fixed plates, and there is in the middle there is one variable plate which keeps moving. So you see that you can understand that at any time, if the middle plate separation can be called D0, then for any position of this plate, one side will be D0 plus delta D and another side will be D0 minus delta D. And if this delta D is small, we shall find approximately that the change in capacitance can also be considered to be proportional to this delta D, which is the motion. So these are the basic sensors which are used for capacitive sensing. The next part is basically signal conditioning. So since we are going to learn, you know, this capacitive sensing arises in various contexts. So but the signal conditionings are mostly uniform. So we shall see in our signal conditioning lectures that how such changes in resistance, inductance or capacitance can be transduced to a change in voltage or current. So that is why we are not talking about it now, but we will talk about it in a uniform manner in our signal conditioning lesson. Now we come to a very, you know, well known sensor which is called the linear variable differential transformer or the well known LVDT. Now this is very much used for accurate position sensing, and the basic principle, it is called a transformer, and a transformer is basically a set of coupled coils. So there is a variation of mutual inductance in this case. So so what happens is that actually there is one primary coil and there are two secondary coils with which both of which are actually coupled to this primary. Now this degree of coupling is actually what changes with the motion. So this degree of coupling obviously depends on the reluctance of the magnetic path. So therefore, if the reluctance of the magnetic path can be varied, then more flux can be of the total flux produced by the primary, some more parts can be linked with the secondary, with one of the secondaries, and less will be linked to another secondary, and therefore we are going to get therefore our induced EMFs. So pulsating flux induces an EMF. So the induced EMF will change in the two coils, and then as we shall see that if we connect these coils in what is known as series opposition, then we can get a signal which is proportional to the motion. So this is a case where this shows the construction. So you see this is the primary coil, and these two are the secondaries. So the flux actually passes like this. So you can see that if the core, this is the core which is actually connected to the motion. So if the core is placed, let us say here, then the flux will actually link much of these coils, while similarly there will be branches here, but when it will return, since these parts are non-magnetic, and therefore if it has to return through this, see here it's magnetic. So therefore the overall reluctance of the path is actually limited to these air gaps, but if it has to come through this path, then it has to go through this much of air gap. So therefore fluxes actually will not prefer to pass through such paths, but will pass through such paths, and therefore they will not be linking the second coil. So as you can see that if the core shifts to the right, then the number of turns of one secondary, more number of turns get linked, while less number of turns get linked in the other. So this is the basic principle of sensing. So their induced EMFs are going to be different. So this is the principle on which now we are going to connect these secondaries into series opposition. Actually, you know, if we have not shown, but there is so if you want to connect them at series opposition, then there is a concept of a dot. So either you connect the two dots, short the two dots together, or you take the output from the two dots and you short them together, then it will be in series opposition. Opposition means that this E0 will actually, if you have an EMF E1 here and if you have an EMF E2 here, then E0 will be E1 minus E2. So E0 equal to E1 minus E2. This is called series opposition. So we connect them in series opposition. So what happens is that obviously, as you can understand, that if the core is above null, null is the middle point, so it is above null, so it is, so one of the, let us say E1, which is equal to, let us say, A sin omega t, plus there will be some, there can be some phase shift also. So if this is A sin omega t, so then because it is linking more number of turns, therefore A1 will be larger, and E2 will be also another sinusoidal EMF, which may be of A2 sin omega t plus phi. So but this A2 magnitude is going to be less than A1. So therefore when you do E0 minus A1, you are going to get one sine wave. If the core is below null, then you are going to give another sine wave. In both cases you are getting sine wave because your excitation is actually sinusoidal, but you can see that if this sine wave can be called positive, this sine wave is called negative, or there is a phase shift. So now, so this is exactly what happens. So you have output for different core positions. So if you see now this output amplitude will also change. So if you just look at the amplitude, then the LVGT characteristic looks like this, that as it moves from the null position, then the amplitude of E0 increases, and in this case also it increases, but there is a phase shift. So now you can see that if you just see the amplitude, you cannot differentiate between a plus x displacement and a minus x displacement. So the sense is lost just from the amplitude. Therefore we have to, when we want to, therefore we have to extract the phase information if you want to know which side it is moving, that is the algebraic sign of the displacement, and that is exactly what is done by what is known as phase sensitive demodulation. So we'll talk about phase sensitive demodulation. This is just one of the circuits of phase sensitive demodulation where you use rectifiers. You can use various kinds of circuitry for phase sensitive demodulation, which is also used in various which is also a communication technique. So we will not talk much about it. We will rather talk about it in our signal conditioning course, signal conditioning lesson. So only we want to say that now using phase sensitive demodulation, what we can do is again we have, so what we can do is that see now if the core is below null, then you get a rectified wave, and if the core is above null, then you get a rectified wave, but which is negative. So therefore now and if you just simply low pass filter this wave, then you will get a DC. So now if the core moves below null, you get a positive DC, and if the core moves above null, then you get a negative DC. So directly from the sign of the DC, you can also see the sign of the motion. So this is what phase sensitive demodulation achieves. It gives you a finally from the various phase shifted AC waves, which are actually produced by the LVDT itself, it it will extract out it will extract out the motion. So, if the motion is in the positive direction, then it will give you a DC signal which is in the positive direction, and if it is negative, then it will give you negative. So, this is now we can actually extend this concept little bit. So, for example, suppose the motion of the core is a slow sinusoid like this. Typically what happens is that the excitation is given at an electrical frequency, something like 100 hertz, 200 hertz, typically 400 hertz. So, so you see the AC is actually a 400 hertz AC, so it is very fast moving, every second it is changing sign 400 times. On the other hand, this motion is generally much lower frequency, 2 hertz, 3 hertz, 5 hertz, 10 hertz like. So, actually what is going to happen is that, so you see this is the motion. So, between at any point, if you take a small time interval, then if you assume that it is actually remaining constant, that is an approximation, then during this time you are going to get an AC, right? You are going to get an AC. So, actually let's look at this. So, actually the I have to change the pen. So, actually if you have, this is very important to understand, that if you have a motion, let us say like this. So, this is the time axis t and this is xt. So, you have, so xt is going from positive to negative. Then what will be the LVDT output? So, the LVDT output will actually be sinusoidal. So, it is going to be like this. Actually there are many more cycles than this, I can't draw that. So, therefore, I am showing it like this, and when this will go negative, then actually this will change phase. Now the thing is that this change phase occurs at nearly 0 magnitude, therefore it can't be seen. Therefore, if you just see the, what you are going to see actually on the, if you connect a CRO, cathode ray oscilloscope to the LVDT terminal, is this. So, obviously you can't make out whether X is positive or negative. So, dynamic, if you now feed it to a phase sensitive demodulator, then the phase sensitive demodulator will actually extract out this wave and show whether the motion is like this or whether the motion is like this, right. So, only thing is that for the phase sensitive demodulator to work well, what is necessary is that the frequency of the sinusoid is much higher than the rate at which this changes, right. So, then demodulation becomes easy. So, to measure dynamic displacement, the carrier frequency should be significantly higher than the highest frequency component in the dynamic signal. So, now we come to, this is another, this is actually not a, this is actually a system whereby a position command can be transferred to a distance using using a pair of machines called synchro transmitter receiver pair. This is also sometimes used in control. Of course, nowadays these methods are becoming somewhat dated, and for transferring motion signals for control other methods are employed. So, we can look at that later, but to understand this, actually what happens is that you have a motor on which you have three coils, and you are going to excite these 3 coils. You are going to excite this 3 coil by a single phase AC. This is the problem. So, we are going to excite this coil by a single phase AC, and you are going to remember that these two are actually at some distance apart. So, what happens is that if you rotate the rotor on the transmitter, then what will happen is that the voltages induced on these coils, are going to be of different magnitude. So, maybe when the coil is in this position, this voltage, the voltage induced here is going to be maximum, and the voltages induced here are going to be less, and so on. So, now these voltages are actually transmitted by cables to another machine which is getting supply from the same AC line. So, it can be shown that if this is applied in the so called stator of the machine, and if the same AC line is given supplied to the rotor, then this rotor will actually move to the same angular position as this. So actually if you move the rotor of one machine, the rotor of the other machine will actually move by an equivalent amount. So by this you can transmit actually a motion command, right. So this is what happens is in a synchronous transmitter receiver pair. This is not exactly sensing, but I mean the but this is one way of transferring a motion command which is also used in control systems. And now we come to Hall effect transducers. These transducers are used quite a lot in, especially in motor applications, where there are, as we will see later when we study drives, that for some motors, for their drives, for example, there is a class of motors called brushless DC motors. So for their drives, you need to know what is the rotor position. So as the rotor is at least at some points of time, at certain discrete points of time, you need to detect that the rotor has come to that position. This is necessary. So this is typically achieved using Hall effect transducers, and the basic Hall effect transducers are also widely used for measuring current, which is also used in drive applications where you need to do current control. But in this case, in today's lesson, we are actually talking about motion control. So therefore, we are going to look at that in that context. So what happens in a Hall effect sensor is that this is a piece of semiconductor through which you can see that some current is being circulated. So this current I is actually flowing through the semiconductor, and so current is flowing, let us say, along one axis. Now on a perpendicular axis there is a flux, there is a magnetic field applied, which is causing a flux density of B. So the magnetic field intensity is, in this case, the flux density which is actually going through the semiconductor is B. So it turns out that if you actually send a current in one direction and you send a flux density, you apply a magnetic field in a perpendicular direction, then along the third direction some potential difference will be developed. This is known as the Hall effect. So therefore, along the third direction, if you connect two terminals, then there you will get a voltage across these terminals, and this voltage magnitude will be proportional to the product of the flux density and the current, right. So turns out, so I mean this is very convenient. So now typically in the case of motion applications, we pass a certain amount of current through it, and then we detect position. For example, in the case of the motor, what happens is that, for example, suppose you put a Hall sensor, this is the stator, and there is a rotor. Suppose there is a rotor, just I am drawing an abstraction. Suppose there is a rotor which is creating a magnetic field. So it creates a magnetic field along this axis. This rotor is rotating, so this is rotating. So whenever this rotor comes to this position where the magnetic field, where the Hall effect sensor is placed, immediately the Hall effect sensor will actually sense that magnetic field. There is already current passing through it. So the moment this rotor will pass through that position, this position is actually very small, so it will just pass through that position. During that time, for a brief time, there will be a flux passing through the Hall effect sensor, and then for a brief period of time it will give a voltage pulse. So this is very much used, widely used in industrial motor drives for for actually sensing the rotor position. So whenever you get the voltage pulse, you know that this rotor has actually passed through a particular angular position, right. So this is the way the Hall effect sensor senses position. Similarly, it so now there are actually Hall effect sensors are used because of various reasons. Main reason, one of the main reasons is that it is very reliable. There is no contact required, and just from a it's actually a non-contact environment, and then there is no moving part in the sensor. So it's so if you just embed it once in the stator, then it's going to work. So this is one of the reasons, and it's very small. Only thing is that it has the level of signals which actually comes from the sensor is low. So you need to amplify the signal. So sometimes, often you get Hall effect sensors with some integrated electronics, so to amplify. So now we come to what is these are this is a glimpse of typical position sensing mechanisms. There are others. For example, there is a just like the Hall effect sensor, there is also a method of position sensing called a magnetic pickup, where you actually put a you put a search coil, and you make an arrangement that as something is rotating, the field passing through that coil will actually change. So if the field passing through that coil suddenly gets linked with the coil, then you will get a pulse again, right. So such pulses can also be used for position detection, but we will but similar coils are actually also used for velocity sensing. So we will look at velocity sensing in that context. So now we come to velocity sensing. So this is what I was saying, that this is a linear velocity sensor. Oops. Yes. So again, it's actually much like the LVDT, except for the fact that now there are two coils. So again, these as this will move, this is a linear velocity sensor. Actually, this is an inductive sensor. So these inductances of these coils will actually change because of the motion of the core. So you can, and this is a push-pull configuration. So therefore the inductance so you can construct, as I was telling, that you can, if you have push-pull configurations, then you can construct a linear sensor. So that's why this is a linear velocity sensor, in the sense that there are actually various ways in which you can do it. For example, if this is a permanent magnet, see in this case what is shown is a permanent magnet. So if you show it as a permanent magnet, then as this magnet will move, then the EMF will be induced in these two coils, and depending on the motion of the coils, these EMF amplitudes will actually change. So this is a case where the velocity, and as we know that the EMF induced will be directly proportional to the velocity of the magnet, because it is proportional to d phi by dt, right. So it is this principle which is used in, so basically this is an electromagnetic induction principle which is used for sensing velocity. Typically, somewhat similar principle is used in probably the most common sensor for sensing motor speed, which is the permanent magnet DC tacho generator. So it is nothing but a DC generator, where again here the case is slightly different. In the previous case, the coils were fixed and the magnet was moving. In this case, it is the magnets which are fixed on the stator of this, and it is the coils on the on the armature which are actually moving. So as they move, they create they give you a DC voltage, and as we know that the magnitude of the voltage is going to be directly proportional to the speed, because the flux is constant. So therefore we have this. So this is a very common instrument which is used. You can also similarly use, rather than using DC tacho generators, which have the DC motors sometimes have some problems, you can also have an AC tacho generator, where you can give and supply an excitation, and if you rotate the armature, then you will get some AC voltage out of it. So it's basically an AC generator, right. So basic principle is the same, that you have to basically change the magnetic field linkage with a coil. So you create some excitation either from a permanent magnet or from some voltage source, which can be AC or DC, and then you see that as you change this excitation, so the flux linked with the coil will change and there will be an induced EMF. So you see that if you have a DC tacho generator, or if the speed changes like this, then you from the AC tacho generator you have what is known as a modulated waveform. So again you have an AC, but the amplitude of this is exactly like the LVDT. Only thing is that in the LVDT the EMF was looking exactly like this, but it was proportional to the position, it was proportional to the motion of the core. Here it is proportional to the speed of the shaft. So that is the only difference. So okay. Similarly, so these are all inductive methods. By the way, there are we might also mention that in many cases, suppose you have a basic sensor which senses position. So if the signal is not very noisy, then you can always differentiate the signal to get velocity, but generally this is avoided, because if you differentiate with noise you will get very huge noise amplification, but it turns out, but you can have various signal processing schemes. Similarly, if you have a basic velocity sensor, then by integrating that velocity also you can generate position, provided you can initialize the sensor with the initial position. So such things are also possible. So in this case, this is also a very simple speed measurement situation, which is often implemented by students in very low cost. So this is one of the ways is is that here the motor is rotating. Suppose the motor is rotating, and on the motor actually you have a disc. So you have a disc. Let's imagine this to be a disc. So the disc is rotating, right? Now on the disc you actually put holes. So you can imagine that this is a disc, and here this is a hole. So you can have a series of holes on the periphery of the disc. So if you look from the front, there are several holes, and at one position you have a light source, right? It has to be you can have an LED, or you can have so now on the other side of it you have you can have a photo detector. So either a photo transistor or a photodiode. So the basic principle is that on these devices, if some light falls on these devices, then they start conducting, right? So what happens is that it is so as the disc will rotate, so therefore whenever this hole will actually pass through the light source, light will pass through the hole and then fall on the photo device, and at that point of time the photo device will start conducting. So every time there is a light pulse falls on the photo device, you are going to get an electrical pulse. Now this electrical pulse can be actually processed by various electronic circuits, something like Schmitt triggers, counters, simple circuits, and then you can actually count the speed, count how many pulses you are getting per second. So so from there you can easily deduce what is the revolution, or how many revolutions per minute is the rotational speed of the motor. This is a very simple scheme of simple optical method. Many variants of these methods are used. Here is a slightly complicated scheme where we use the concept of correlation. So this is a case where we are trying to measure the velocity of a hot strip. So it turns out that that when you are in a rolling mill, where you are trying to feed a thick bar of steel through two heavy rolls, and when it is passing through the roll gap, it is actually getting thinner. So, you are reducing the dimension by rolling. This is a very important mill which is there in almost all steel plants. So, in hot rolling, this bar which is getting rolled is actually red hot, right. So, you can imagine it is very high temperature, and therefore, as we know that we need to sense the speed from a distance. We should not go too close to it. So, therefore, for example, magnetic sensors may not work at a very high temperature. So, what we are going to do is that we are going to now, you might think that if the rod is hot, then it itself emits light. So, when we are talking about optical method, it is not that we are going to always talk about light in the so called visible frequency range. Sometimes we apply lasers, or light in different frequency ranges, different wavelength light. So, and we can also have detectors which are actually sensitive to certain narrow wavelength bands. So, if the hot strip is not radiating in that band, then we do not have any interference from the radiation of the hot strip. So this must be remembered. So, having said that, let's look at the fact. So, now you see what we are doing is we are actually so we are actually taking the signal from two channels. One is xt, another is yt. So, even if our signal, so we have suppose imagine that we are actually receiving radiation from one channel. Now, this radiation will actually depend, this radiation pattern will be probably varying like this. Now, so the radiation sensed by these two signals are going to be delayed. Actually, the basic premise is that the radiation pattern from a particular part of the of the strip is going to be, although its shape may slightly change and the signal is going to be erratic, but it will over a small distance it is going to preserve its shape, and therefore we are going to have as it travels, when we take the signal through the second set of, when we take the signal through the second set of sensors. So, what is going to happen is that the correlation, the signals received here are actually going to be a time shifted version of the signals in this channel. So, the basic premise of this measurement is that the signals yt are actually noisy versions of xt, but time shifted. Now, how much time shifted, that we do not know, that actually depends on the speed, since this distance d is fixed. So, therefore, by how much time shifted they will be, that will depend on the speed of the strip. So, now we are going to determine precisely that. So, what we do is for that, so if you have two time shifted signals, roughly time shifted, they may be slightly different, then there is a technique of correlation. So, if we compute, let us say say T1 to T2 xt to yt minus tau dt. So, we time shift x, and so x we are measuring. Suppose we time shift, in this case as it is shown that x is time shifted. So, we time shift x, and okay, so in this case let us say we time shift x and we keep yt. So, we time shift x and then we multiply it with y and then integrate. So, obviously, if the maximum, it can be shown that this correlation function, this is actually a function of tau or xy tau. This will achieve its peak so we gradually vary tau and then start plotting this function. So, wherever this function reaches the peak, that is actually the tau which is required, that is the time required for this strip to travel this distance d. So basically tau d by tau is the velocity, and since d is fixed, so by computing tau we can get v. This is called a cross correlation method of measuring velocity. It is also used in flow measurement in the case in what is known as cross correlation flow meters. So we are moving fast and we are giving you glimpses of various kinds of measurements. So one of the advantage, what is the advantage of this is that if you use powerful light sources and if you use powerful sensors, then you can actually do the measurement from a distance, and temperature does not affect these measurements too much. Now we come to, so we have seen some methods of velocity sensing. Now we come to acceleration sensing. Acceleration sensing is not very much used in the industry, not too much. I mean, compared to that, velocity and position sensing are much used, and this is a typical configuration of an accelerometer, which is so therefore, in fact, acceleration sensing is mainly used in the industry in the context of vibration sensing, which is a sensor which is widely used, especially for maintenance and fault diagnostic purposes in all kinds of machines. So piezoelectric sensors are basically, in a way, they can be called acceleration sensors. So that is the biggest class of acceleration sensors which are used, but just for a general principle, this is an electrodynamic accelerometer, in the sense that you have in such electromechanical or rather electrodynamic accelerometers, you have a mechanical part and you have an electrical part. So the mechanical part is generally a mass spring damper system, right? So you see you have a permanent magnet and you have these two springs. Additionally, damping is created sometimes by putting in oil, because that will give you viscous friction and that will give you damping, and there is this coil, right? So it turns out that as this, so if you give, now this accelerometer is actually put in the surface. You are interested in actually measuring the acceleration of this surface. So as you can understand that if this is actually sort of floating in maybe oil using these two springs, so you can understand that if this is actually sitting on this surface, and if this surface is actually accelerating, then this mass, which is sometimes called the proof mass, is also going to vibrate. So you are going to get a signal which is, so now that will induce EMF, right? Now it can be shown that this EMF induced can especially in certain frequency ranges, this equipment can be so designed that this EMF is going to be proportional to this acceleration, right? So this is one basic technique of, so in many accelerometers you will find that there is this concept of this mass spring damper system, which is connected to either a position to resistance sensor like a potentiometer, or it can be connected to other kinds of position to for example in this case velocity to voltage sensor. So this is actually a rotational version of the same, where previously the proof mass was rotating like this, now it will be moving inside. So you have some tension spring. So again, I'm sorry. So again you have some springs. No, this page is changing. So anyway, again we have this rotor which has some moment of inertia, which is the rotational equivalent of mass. We have damping oil which gives you friction, and similarly we have some torsional springs. Actually these are they're torsional springs. So you again effectively have a mass spring damper system, but now in rotational terms. So you can have both. We'll skip this slide. This is what is known as a closed loop measurement method. We'll actually skip this slide. Now we come to the piezoelectric sensor, which is the main sensor used for acceleration sensing. So it turns out that certain solid materials, if they are deformed due to force, then they actually across their dimensions they actually generate potentials. They actually generate charges and then they generate potential. So this is called the piezoelectric effect. And these typical materials are, there are synthetic materials, there are some what are known as polarized ferroelectric crystals, and there are some natural materials like quartz. So so as we will see in the next figure, what happens is that if you, so suppose you have the crystal cut in this shape, and we are only showing one dimension. So there's basically a crystallization structure. So when if you put force on it, then that crystallization structure becomes deformed. So when it becomes deformed, it actually generates an electric field inside, and that leads to accumulation of charge on the two sides, and obviously that will give you some voltage difference, because the electric potentials become different at the two ends. So it is this voltage difference that is to be sensed, or the charge which is to be sensed, right. So if you see the equivalent circuit, then this device can be seen as sometimes seen as a charge generator, and why this is happening. So the model is that it can be seen as a charge generator in parallel with the resistance. Cry means crystal. So in parallel with the resistance and the capacitance of the sensor. This is the leakage resistance of the sensor, which is generally very high, 10 to the power 12 ohms, and C, the capacitance is again, this is essentially like a parallel plate capacitance. So it is given by epsilon A by T. A is width into length, so therefore epsilon WL by T. Now this crystal will now generate a charge and a voltage, or a voltage, and it has to be sensed. So it has to be amplified obviously to some voltage which is measurable. So this crystal is to be connected by a cable. So now it turns out that the moment you connect this cable, this cable also has some capacitance. So because of this capacitance, the circuit, equivalent circuit previously, which was C crystal and then R crystal, now this C and R will change, because the cable, if you have a long cable, then you have a distributed capacitance to ground. So now this capacitance will actually come in parallel with the crystal capacitance. Similarly, this amplifier resistance will also come in parallel with the crystal resistance. So what will happen is that it turns out that if you are talking of a force, and if we say that the charge generated is actually proportional to the force applied on the crystal, then dynamically you can see that the EMF generated by the force is like acceleration. If some mass is actually accelerating, then the force applied on the crystal will actually be proportional to the acceleration. So therefore you can see that the amplitude of the output voltage, not only that the time constant of this transfer function depends on RC, but its sensitivity also depends on C, right. So if the C changes, so if you now connect a higher length cable, then its sensitivity is going to change, which is a very undesirable situation. So therefore this is the first point. The second point is that this is a high pass transfer function. Therefore DC forces, constant forces, if you apply a constant force, there is not going to be any EMF. So therefore these kind of sensors are not used for measuring constant forces. That's why they are used for measuring vibration, where you have high frequency oscillations. So it is not possible to measure static force with this circuit, and static sensitivity will change, as I said. So we often use a circuit which is known as the charge amplifier. So it can be shown that in this circuit, because of the fact that this potential is actually at 0, because of the virtual ground property of the operational amplifier, it can be shown that this circuit behavior is actually independent of this capacitance. So the static sensitivity you can actually variation in static sensitivity can be avoided. So, that is why charge amplifiers are widely used with piezoelectric crystals. So, basically we have, if you have the in piezoelectric crystals, we have the acceleration which is sensed by a seismic transducer. So, the seismic transducer mass actually applies a force F on the crystal. So, this creates a displacement depending on the spring constant, and that creates an EMF. So, that this EMF is now to be processed by a suitable circuit like a charge amplifier. So, this is what we have briefly covered. We have basically taken a glimpse through some methods of position and velocity measurement which are used in the industry. So, let us look at a summary. So, we have looked at position sensing, and we have seen inductive, resistive and capacitive ways of position sensing. We have seen velocity sensing, we have looked at electromagnetic methods of velocity sensing, we have looked at optical methods of velocity sensing. And we have seen acceleration sensing, where we have basically looked at piezoelectric and also one electrodynamic method. Okay. So, this has been a quick view through motion sensing. Coming to points to ponder, what are the main advantages of inductive and capacitive sensor over resistive ones? So, you can understand that it is very clear. Why should the carrier frequency of LVDTs be high? So, you can again try to figure out that what happens if the carrier frequency is low. In what situations are optical methods of speed sensing useful? This is also an interesting question. And finally, why you must use a charge amplifier rather than a voltage amplifier with a piezoelectric crystal. You can try to look for these answers, and then I think you will learn slightly deeper. So thank you very much. We end here today.